Right, hello. So my name is Juan Pereiro. I'm a lecturer in Cardiff University, and I want to talk a little bit about my main activity, research activity in Cardiff, which is the low-energy electron microscopy of semiconductor material. And I'll explain a little bit what this is about. We live surrounded by electronics. We are constantly interacting with the computer or with the PlayStation or with the phone or with a car, which actually has quite a lot of electronics in them. The electronics that surround us is actually not going to disappear, but will keep on increasing and eventually slowly make our life different, hopefully easier. And there will be more change as the change that we have seen in the last few years. For example, with the appearance of the Internet of Things, the communication just not between people, but between items, right? So the cars will connect with each other and enable us to have driverless cars, or our fridge will order food when we are running out. We won't need to worry about these things. So we will have healthcare at remote healthcare facilities. So the evolution of electronics will actually affect quite a large number of industries, as the ones that I have in the slide. For example, automotive, healthcare, or communications, or robotics, or aerospace, and so on. The electronics, all the electronics that we have around, are based on a particular chemical element, which is called silicon. The thing, or the special thing of this element is that it's a semiconductor, and then it allows us we can control whether this material conducts electricity or it doesn't conduct electricity. And it allows us to make very, very, very small switches, electrical switches that either allow us to conduct electricity or not conduct electricity, and this conducting or not conducting allow us to have these 1 and 0s, either a 0 or a 1, that are the building block or the foundations of computing. So that's silicon. That's the material that we have. In 1965, Gordon Moore wrote an article. Gordon Moore was a co-founder of Intel, and wrote an article talking about the future of the electronics when the electronics were actually, the computing was starting. And he said that the number of components in integrated circuit would increase, or would double every year from there on. And he was thinking about the 5-10 years after 1965, but it actually has held until today. You can see in the graph, all those points represent one particular chip, computer chip, and the y-axis is the number of these small switches that I was talking about, the transistors, the number of small switches within a computer chip. And on the x-axis is just the year. And what we can see is that it has actually been growing. It has been doubling every year until now, and now we are starting to see a slowdown of the growth of the electronics. And in order to keep that development, because we want to keep developing electronics in order to keep on helping us, let's say, in order to make our lives easier, as all the electronics that we live with today have done. We are looking at new materials in order to at new ways of making computing and new ways of transmitting information. And therefore, we are looking at compound semiconductors. You may have heard about compound semiconductor because there has been a very large investment around South Wales And in particular, we are looking at 3,5 materials, and in particular, gallium arsenide. 3,5 materials are compounds of one element of the group 3 in the periodic table and one element of the group 5 in the periodic table, and you have it in the slide. For example, in gallium arsenide, the group 3 element would be gallium, which is a metal, and the group 5 element would be arsenic. So we would have a compound which is called gallium arsenide, and it's also a semiconductor as silicon is, but with a particular characteristic that it actually can emit light. And what we want to do is to have switches, but it's not a switch of electric current, as in the case of silicon, but we want to have a switch of light. And then we can do computing with light, we can do electronics with light. And those electronics will be faster, more efficient, and more powerful. And we can keep on evolving the electronic systems, our technologies. Semiconductors are these materials that I'm talking about, semiconductors, either silicon or gallium arsenide, they are crystals, right? And what a crystal means, what I mean by crystal is that the atoms are arranged in a periodic fashion across. So we have a building block, like you have in the slide. On the left, you have the silicon. In the middle, you have gallium arsenide, and that periodic arrangement of the atoms extends over the whole of the material, effectively, right? So that the square is effectively your building block, and then you put a square next to a square next to a square, and then you build the whole of the crystal. What we do with these layers is to we create these crystals in different layers, and we can in order to make devices. And with these devices, and as well, you see one example in the right, they can actually be very complex. How we do it, how we build these devices, how we put these building blocks, these atoms arranged in a periodic fashion. We put them there. We create a new layer, and how do we do this? Is through a process called epitaxy. And this is what I'm going to try to explain. I have a little video. What it consists of is we have a crystal, right, which we call substrate. It is already formed. So we have our atoms arranged in a periodic fashion. And then we are going to have a bulk material, a piece of silicon, or in the case of gallium arsenide, a piece of gallium and a piece of arsenic. We are going to heat them up, and we are going to evaporate those materials. And then we are going to evaporate those materials onto our substrate, right, or onto the crystallizer. What is going to happen is that when we evaporate, there are atoms that come out of these materials. We are going to create a beam of these atoms. Let's use the silicon as an example. So we are going to have a crystal-ready form of silicon or something else, but a crystal-ready form. And then we are going to have silicon. We are going to heat it up. Atoms will come out of the silicon. We are going to create a beam of those atoms. And those atoms we are going to focus them on our substrate, on our already formed crystal. When those atoms arrive to the surface, because our substrate is going to have a certain temperature, usually quite high, the atoms that are arranged to the surface are going to have a little bit of energy to move around. Some will leave, some will not, some will stay moving around, and eventually we'll find a position where their energy is minimum, or the lowest possible energy, and they will stay there. And in this way, we will form new layers of material, similar to what the video is. Obviously, this video is just a simulation using lentils. It's not a simulation. It's an animation using lentils that I have done, but I actually have a more advanced video that actually simulates with the actual physical parameters. It can simulate how the atoms behave. And what I wanted to illustrate in here is that actually once the atoms arrive, there is no particular way they are going to behave, or the new layer is going to grow. It will depend on a number of factors. It will depend on the temperature of the substrate. It will depend on how much material we are evaporating. It will depend on the other material, if there is any other material present around, or it will depend on the pressures that we do the experiment at. So there will be a number of factors that regulate how the growth goes on. And there are the 3 examples effectively in this simulation that could happen. There are more ways, but these are 3 examples. In the first example, what we have is atoms that arrive on the surface and they form clusters. The atoms are going to always prefer to be as surrounded as possible. They are going to want to be surrounded of as many atoms as possible because they feel more comfy there. And if they feel more comfortable, feeling more comfortable usually means that you have less energy. You are more relaxed. So in the case of the atoms, that's what it means. They are going to try to have more atoms around. So if if the atom has 1 atom on the side and 1 atom below, it's better than if they just have 1 atom below. So when the atoms arrive, a cluster will be formed. The atoms that arrive will prefer to join the edge of the cluster, and then these clusters, effectively, that are only 1 atom high, or its height is only 1 atom, they will grow until they all coalesce and they form a new layer, and then new cluster will be formed on the new layer. The new cluster will grow another layer, and so on. Sometimes it happens that our crystals have, because we cut them like that, or because we have prepared them in some way, our substrates have already steps, so we prepare them that way. And what that makes is that all the atoms that arrive will join the steps. So what we will see is that our steps will actually grow, and effectively what we see is like the steps are flowing in one direction, but what is happening is that we are creating new layers as this, which is reflected in the steps effectively flowing in one direction. The last type of growth that this simulation shows is what happens when the atoms that arrive onto the substrate, they don't have much energy. They cannot move much around. So what happens is that they form clusters, but because they cannot move much around, they are not going to be able to reach the edges of the other clusters, so they just keep on growing, and they form these big blobs or big mountains, roughness around the surface. And sometimes that's what you want. Sometimes you want to grow one way, or sometimes you want to grow the other way. It depends on what the device that you're trying to achieve requires, right? So that brings me a little bit about what I do. What I do is low energy electron microscopy. So we image samples using electrons. So the using electrons allows us to see smaller things. Effectively, it allows us to see features on a sample that are 1 atom in height and around 10 atoms in length. But the unique feature of this microscope is not that we use electrons, because there are lots of different microscopes that use electrons. Is the fact that we can make movies of the processes, right? So we can grow crystals inside the microscope, and we can make a movie of how the crystals are growing. And therefore it allows us to create understanding on whether the crystal is growing in one way or the crystal is growing in a different way, and so on, and create knowledge that will allow us to grow new materials or new structures and so on, in order to generate to be able to eventually create new devices and new functionalities. This is an illustration of the what is different from our microscope with respect to traditional epitaxial growth, right? So traditionally, what people do in manufacturing is if you want to grow a new material or a new device, what you do is someone tells you, I want this kind of structure in order to grow a new device. So you devise your experiment, you grow your set of samples, then you send that samples to a colleague. They will look at how the atoms are arranged. Another colleague will look at how the surface is, and then you get all your information, and you decide whether you want to change your conditions, and then you keep on going around until you get to the samples that you have been requested, and then those samples will eventually end up in a device and so on. In our system in Cardiff, we have everything in one place, and we can actually look at the samples during the growth. So we don't need to go around and around, but we can see at the same time that we are growing whether we are achieving what we wanted to achieve or we aren't, and then we can change the conditions. So it effectively accelerates the process and creates understanding. The last slide is effectively just to show you a few videos that we have recorded very recently. In the first case, we have two representations of the same thing, one in black and white, one in color. The color represents the different arrangements of the atoms on the surface, right? So if you have yellow, the atoms will be arranged in one way. If you have red, the atoms will be arranged in a different way. If you have blue, the atoms will be arranged in a different way. On the left, you have a droplet of metal, and that metal will when we start the experiment, that metal will diffuse, will move across the surface, and that will generate growth of material and changes in a structure on the surface. So it just shows how we can see in real time changes in the structure of the surface. We can see growth and so on. So it illustrates the ability of our microscope to do this kind of work. It illustrates how our microscope effectively is unique. I want to highlight that the microscope is actually unique worldwide. It's the only microscope that can look in real time at these processes for these particular materials, for the 3,5s. There is no other microscope in the world that can look in real time to these materials. The second video actually illustrates the appearance of a surface that wasn't stable. So a new type of surface pops up and disappears, and people thought that these surfaces were actually stable, but they are not. So there are patches of material that have a different structure here and there, and the patch appears and disappears. And the last thing is just to illustrate what we do once we have to the observations. We don't just say, well, we have observed this, but we try to understand it, and we do a model of what is happening on the surface. And what we are seeing in that last video is to how at low temperatures the processes are a lot. The surface has less. All the atoms in the surface have less energy, and the processes are a lot more rough. The surfaces are in general more rough, right? It's similar to what we were seeing in the previous simulation, right? That the atoms cannot move much, and then you end up with a rough surface. So in this case, it's similar. And as we increase the temperature, the surface is a lot smoother. So I just wanted to transmit that how we work with our unique instrument to enable us to understand what is happening on the surfaces, and that will ultimately enable us to grow new materials and build understand. So to build understanding, to enable us to create new materials and new technologies that hopefully at some point will make your lives easier. And that's all I wanted to say. Thank you very much. And I hope I will see you soon in Cardiff.